Good morning. Welcome to this panel today on AI networking and themes that are important in the context of AI networking. I have to say, the last year, 2 years have witnessed more change in transport technologies and AI networking than it feels the entire decade before that put together. I'm extremely grateful to you all for joining us today in what I hope will be a very interesting dialogue on themes that are driving sort of AI infrastructure efficiency and how the fabric impacts that. I'm thrilled to be joined by my colleague Balaji, founder of Clockwork and professor at Stanford, as well as Roy Chua, distinguished in the analyst industry, deep expert in networking and hosting the panel today. So thank you all for joining us. Roy,
Excellent.
do you want to just take over?
Yeah, let me just go do that. Thank you, Suresh, and thank you, Balaji. It's definitely a pleasure and an honor to be on a panel with both you guys, given your extensive experience in the industry across infrastructure technology, including networking, obviously. So I'll just start by saying that we just published our data center networking report. That's our third edition, and that report has gone through many iterations over the years. It started out focusing on smart NICs and then been migrating its way into the full data center network. And the reality is now that the data center network is a complex beast. It's not just the typically what we look at as Ethernet and what is now scale out, right? But it's evolved into a scale up network, powering XPUs, GPUs, your typical scale out, but now that's your front end and which is the network that we used to be used to, which is the cloud network, and then the back end, which is the network that's used by the XPUs and GPUs for talking to each other. And then across, because one data center can't contain the workload, we have to spread across multiple data centers. And what used to be long distance, data center interconnect or DCI is now scaled across in a large campus full of data centers and full of GPUs. And so seeing a lot of evolution there. And the reality is, I don't think that's going to stop anytime. What we're seeing is the capex commitments keep going up, right? So if you look at the top, four, five, six hyperscalers and frontier labs, the amount of capex that's committed keeps going up. When we wrote a report, it was 620 billion committed for 2026. It's gone up to now 720, 740. The number keeps going up. I mean, it's like the number go up philosophy, I guess. That's the more is better.
And I just heard a report saying the projection for next year is over 1 trillion.
So the money comes from somewhere. I'm not sure where it comes from, but I wish we could get. I just want 0.1% of it. That's all I really want. But, but, but fundamentally, it keeps going up, and that's great, right? But what we're seeing at the same time, despite all that investment, is that the effective utilization, right? The amount of the GPU compute that's actually advancing, the model building or the inferencing is a much smaller percentage of that, right? 20%, 30%, 40%, whatever you believe, whatever your optimizations are. That's we're not using anywhere in the 80, 90, 100% of all that money that we're sinking into the data centers. And so there are multiple limitations for sure, right? You can improve many things efficiency wise, but one of the easiest targets, one of the potentially lower hanging fruits we all believe collectively is the movement of data, meaning networking, right? And whether you're talking about scaling up or scaling out or scaling across, the network can get in the way or the network can help you depending on how you've architected it, how you design it. And so one of the key questions we'll be talking about today in this panel is the network. And there are many ways to improve the speeds of network. You can keep improving the speeds and doubling it every single time, sure. But there are principles that we can apply regardless of the speed of the network, whether you're running a 200 gig, 400 gig, 800 gig, 1.6 tera, 3.2 tera network. There are principles that should apply in basic design, in basic management, basic orchestration of the network that will bring value regardless, right, over the next many, many years. And some of the three themes or principles that I'm hoping to discuss today and actually learn a lot about, from Suresh and Balaji, and we'll discuss here. The three themes are going to be first, network observability and the importance of network observability. We want network observability to be a first class concern. It isn't always the case. We're usually so busy in getting those optics connected and buying those cables and plugging everything in and trying to make sure it's all plugged in. And then we turn it on and it doesn't quite work. Why? We have no idea. Let's plug it in again, right? So observability is one of the key things that I think everyone's realizing the importance of. Um, and it's across all domains, whether you're talking about pre-training or fine-tuning, right, reinforcement learning, or inferencing. I think that's critical, or even scale across, right? I think that's one of the key elements. So network observability. The second one we'll be talking about is this concept of fault tolerance versus failure recovery. Networks fail, XPUs, GPUs fail, right? Servers fail. And when they fail, something bad happens to the workload. And sometimes we confuse fault tolerance and failure recovery. We're like, oh, look, I can get recovery really quickly. That's great. Or, hey, this thing is fault tolerant. I'm perfect. I don't need to fix anything. Is that true? Is that not true? Well, obviously it's not true, but we'll talk about that as well. And there is the tolerance in the network level, tolerance at the workload level, recovery at the network level, and recovery at the workload level. And again, they are different. They can complement each other, but that's a discussion that we should have around that. And then finally, the third theme here is the workload awareness and context as part of network design. When you're designing a network, it needs to be in context of the workload you're trying to support. I mean, we know that certainly. Why else would we have a scale up, a scale out, and a scale across network and the front end and back end networks? Because it's sort of fit for purpose. What is that purpose? What are the key considerations? We're not going to go into every single thing here. We only have about 45, 50 minutes. But I think we can surface some of the key concerns or the key design elements here, given the expertise that we have here on the panel, and have a conversation around that. And certainly, if you want to learn more after that, you're welcome to contact Clockwork, and that's where all the experts sit, and hopefully you'll get value from today's webinar. So let's get started. But before I do that, let me just see if Balaji or Suresh have anything to add to that introduction here.
No, that was a wonderful introduction, Roy.
Well, first of all, I just wanted to say hello to everybody. I'm looking forward to the conversation. I think you've summarized the main points, Roy. Let's get stuck in it.
Okay. All right. Let's talk about network observability. And so, we have these three coupled domains today, and we'll just leave it at fundamentally GPU, XPU network. We'll leave the cloud front end thing aside because the principles will apply there as well. But we have our scale up, our favorite NVLink, and then the upcoming competitors, UA-Link and ESUN. We have scale out, which we used to bring in InfiniBand, but now we don't talk about that as much as we used to. In fact, we don't talk about it at all. We just talk about Ethernet, right? And NVIDIA still talks about both, but a lot more Ethernet today. And then scale across, which we'll deal with. That's Ethernet, but that's usually optics and fiber, and we'll talk about that. Each of them have different traffic patterns and failure modes and sort of visibility gaps. So some of the key things I would like to discuss is, as the infrastructure starts splitting into these things, up, out, across, right? What are the important visibility gaps that we're seeing based on your experience? And I'm happy to share as well based on our conversations with customers and clients as well. What kind of failure modes are the most damaging in these kinds of clusters? And let me see if Suresh or Balaji, you want to start first, and then we can have a conversation, and then we'll just keep progressing on the topic itself.
Yeah, I'll start, and Balaji, feel free to chime in. But I guess I'll start by saying, when you think about these three kinds of networks, right, it's important to start with an acknowledgement that all three are essentially solving at the highest level one common problem. How do I get a large number of accelerators to work together and essentially deliver whatever the outcome is that the workload is seeking, right? All of them are trying to basically create one gigantic computer out of many smaller computers is one way to think about it. And when I break that down, then it starts to say, okay, the difference between these really boils down to when I'm really managing distributed state and data movement, how do I decide which topology really deserves what kind of state transfer and what kind of data movement? So if I'm doing a training job, I might say my dense collectives that are, let's say, an all reduce or a scatter gather operation in a tensor parallel group might need to live in a scale up domain. I might basically say for data parallel computations and training again, I might be comfortable using scale out as the domain across which I'm having lots of data replicas that are maybe synchronizing collectives at the end of each iteration with an all reduce operation. And if I truly am going across buildings in a scale across context, then I might want to use that for things like maybe synchronizing checkpoints, or if I'm doing asynchronous gradient exchanges, that's once every few iterations or so, that's what I might use them. So it's important to say what changes as you go across is really how I'm optimizing the placement, the way that state is exchanged, the way that data is moved, depending on what domain I'm living in, right? And therefore, if I think about failures, it all starts with saying, how is my workload being impacted by the kind of failures that are really common across? I might watch for different things. For example, in a scale-up domain, I might be really concerned about NV-link failures. In a in a scale-out domain, I might be concerned about sort of congestion as much as I am about potentially gray failures and link flaps. But if I step back, I would start by saying that failures tend to be local. Their impact on the workload is what we really care about. And there's a class of failures that seem to be sort of common across all three, starting with perhaps the most common being gray failures, link flaps being common across all of these, right? They seem to impact all of these.
Agreed. I think, what we do see is, and unfortunately, at the UA link, at the NV link level and scale up, the amount of stats that you see are quite limited. I mean, if you look at it, I mean, if you pull up
Right.
your little observability window, right, that NVIDIA gives you, you don't see that level of details, generally speaking, because most of the time, the connections do work, and
Right.
it's a sort of a direct connect, right? Sort of, and there are less complexities in there, unlike a scale out where you have multiple hops, right? And you have to deal with that. So, but you are absolutely right in terms of there are possible failures across all domains. Um, Very often, what we see is just because of the sheer number of nodes on a scale out. That's where we tend to focus our attention on. Um, and in a scale up situation, yeah, there are failures, but perhaps there's less other fixes that you can apply to the problem, short of swapping out and say, yo, that's just broken. Let me just fix the whole thing by swapping it out, right? As opposed to maybe in a scale up domain where you can take some steps to deal with or tolerate the faults in the temporary measure to do that, right? And I think that is one of the difference because when we talk to the clients and when we talk to data centers, very often the attention tends to focus very quickly on just the scale out domain, right? We don't hear people talking about, what can we do to fix NV-link failures typically, right? And
Yeah, no, that's there's a good reason for that, right?
yes,
Uh, the way I see it is, as a networking person, scale up is just a fully connected switch.
yeah,
There's 72 GPUs or however many, and then
yeah,
there's one fully connected, basically shared memory or output queue switch. There's nothing, it's pretty robust.
yes,
And scale out is the one that's what you would think of as a genuine networking problem because
yep,
you have multiple hops and you have to worry about contention and congestion and failure of links because that's a problem at these high speeds. And
yes,
scale across is again somewhat more conventional networking where there's some pipe connecting a couple of locations. I mean, it's more familiar, let's say. Okay.
yes, yes,
And but I think what helps in the scale out world, in one sense, and that is what makes it particular to this workload and what makes it amenable to interesting designs is the fact that there's this sort of rail-oriented style of communication between GPUs. And yes, you can go across by, do NVLink transfer or you go, super spine or
hmm,
what's called, I guess, core switch and hop over. Yes, those things can be done and are done, as needed. But primarily the rail-orientedness rules the scale out, the way the traffic is exerted on it. And I think, there are good solutions that you can then come up with, given the nature of traffic being what it is. And people have come up with some interesting ways of doing it. And the way I see it is that This will continue. I don't think, where we are now, whether it's MRC or UEC, will be the final word. They'll continue to tweak, and we'll learn to what the deficiencies those things are. But at the end of the day, maybe in a few years, we'll all come back to plain old Ethernet and do the thing we've done, which is to throw more redundancy in the fabric. Let the fabric never get oversubscribed. I mean, let it always be undersubscribed, right? So that's one way of having redundancy and dealing with Ethernet headaches. But I think, it's an interesting time. And,
Hmm.
this has happened many times in networking. I remember storage wanting to get onto Ethernet. That led to the data center bridging standards.
Yes.
I worked with various people on it, right, very enthusiastically, and it was defining some of the research I was doing for a few years. And a lot of interesting lessons learned. I mean, technically, there were very interesting questions and challenges.
Hmm.
Drop-free networks was so alien to my colleagues in the IP world. What do you mean a network shall not drop? Okay, and so on. And the end-to-end principle versus the in-network stuff. So these
That's
things
right.
tend to come in cycles, um,
Hmm.
and they have benefits. And when solutions come, we should be happy. Then we
Yeah.
should start to improve them, I guess, right? So
I think that
One
that's.
one comment I would make, Roy, on is the one thing that is unique. So you're right that failures are maybe there's not enough visible. I think two comments. I think as there's not enough telemetry on within a scale-up system to know as much as there is in scale-out, right? And certainly
Right.
NVLink. But one thing that makes that problem particularly more severe is the blast radius in the modern rack scale systems,
Yes.
particularly with the GB200, GB300 systems that are perhaps the most mainstream of the big scale-up systems that we're now seeing. The failure of an NVLink's backplane can cause multiple trays to be taken out, or serviceability of a tray could cause the rest of the workload running in a GB200. And so I
Hmm.
think the emphasis on the one hand, there's a question around what is the visibility into what's going wrong.
Hmm.
Perhaps the greater emphasis is can I really stay fault tolerant at a workload level when something goes wrong within a scale up system? Because the blast radius of a failure is very significant. In fact, when
Hmm.
we deployed a live GPU migration solution, the greatest interest was in understanding if I can use the compute trays within a rack scale system to really fail over and keep training running continuously in the face of failures. And so that maybe that's an interesting, an important distinction to
Yeah.
call out.
Yep. I think that's important because yeah, the blast rate. I mean, fundamentally, that your NVLink, 72, 144, right? That is the so-called unit of compute, right? Before you
Right.
hit the scale-out
Indeed.
network, and if the failure takes that out, that's a lot of money that's
Indeed.
wasted at that point in
Indeed.
time, right? And
Indeed.
that's
yeah, I think the way to think of it as well for me is that scale up is the compute tends to be the fragile component. The
Mhm.
network is pretty robust.
Yeah.
And in the scale out, compute, yes, it's still fragile, but comparatively network, compared with respect to scale up, the network is a lot more parts, a lot more
That's
parts that can fail.
a lot more humans plugging in those optics,
There's that too.
so and that is so speaking of that, right? So I think one of the things that I think we talk about observability, but there's observability during the training run or during the inference run or whatever it is. But one of the things that I do know is that when I talk to some of these neoclouds, bringing up the entire cluster the first time tends to be a very difficult thing, right? Just the first time bring up, and then once it's running, they don't want to touch it, right? And so one of the questions I do have is, what's your opinion on ensuring the fabric health before the job actually starts, right? Versus ongoing observability and the ability to fix problems as they're running. And what are you seeing? I mean, as clockwork, as you're working with these different data centers and neoclouds, what are you seeing in terms of the desire to know fabric health in advance, right? Even
Yeah.
before the job starts. Yeah.
Yeah. Yeah. I mean, I'll say a couple of things, right? So the first, almost every neo cloud that's building up large clusters to hand off to tenants has invested obviously in sort of pre-deployment audit of their fleets. And what is very clear, we've probably worked with a few dozen neoclouds. What is very clear is that there's a fairly large gradation in the level of sophistication of tooling that various neoclouds or on-premises enterprises have in their ability to audit the fleet even before they hand off to a tenant, or in the case of an on-premises enterprise, before they start running jobs, whether it's training or inference jobs, right? So the degree of many get to the basics around things like, let me use DCGM to test health of GPUs.
Yeah.
And so there's a whole common denominator of good pre-fleet audit tests that are sort of that most people are running. And now there are open source tooling that NVIDIA themselves have created that's starting to raise the floor on what tests are available that I can use to make my GPU cluster healthy before handoff. I think where we find, in fact, we have built several tools, and the places where we find there to be great variability and great value is, am I actually running really workloads that stress collective communications and suss out problems in your fabric, problems that could stem from bad topology, problems that could identify grave failures that are harder to detect, et cetera, right? And so it's really the advanced tests where you're running mock workloads, where you're really teasing out maybe second order problems in the fabric before handoff, where I think there's the greatest difference between really sophisticated clouds and not so sophisticated. But I think this is not, to me, in the end, this will be something that will people will catch up as open source tooling is starting to arrive at a fast pace in this area.
Yeah, especially as the fabric itself becomes more intelligent and you have in-network collectives that you may be wanting to test because the switches
Indeed.
are participating in that, right? So, with NVIDIA's Sharp or eventually with UEC's UET, there are in-network collectives options, and the network needs to be stress tested accordingly as if
Right.
it were a real
Right.
workload, and it gets more complicated at that point in time, right?
Indeed.
Yeah,
Indeed.
no, I think that's fair. So, at this point, I want to sort of move on to the next theme here, right? We talked about observability, we talked about some of instrumentation, we've talked about the observability of the different domains, and Balaji brought up sort of the what we believe to be the failure modes driving the need for observability across the three different domains, and I think that was very elegantly put. Um, Now we talked about MRC and UET UEC, which I'm sure the audience is all quite familiar with. But let me just describe what that is before we go on to the next one, right? Which is so everyone on the webinar is likely familiar with Rocky V2, right? So it's RDMA over converged Ethernet. Is a way of running RDMA workloads over what we like Ethernet fabrics because we're used to them, we know how to manage them, and we view them as potentially more cost effective. And if what we had thought collectively was that we would do the Ultra Ethernet Consortium with Ultra Ethernet Transport, which is the potential successor, we thought, to Rocky V2. At least that's what many of us were thinking. And then all of a sudden, a couple of weeks back, we have this new thing called MRC. And that was it's a standard because it's under OCP now, I guess. When they were playing with it, it wasn't, but that's an OpenAI, NVIDIA, Broadcom, AMD, and you can see the list of the different organizations that have participated in it. It's an interim step between where we are with Rocky B2 and UET UEC. At least that's the way I view it. And they've taken some of the concepts, many of the concepts, in fact, from UET and moved them forward, making them available on pretty much today's networks today. Right now, with a couple of commercial NICs out there really supporting it, right? So Broadcom's already talking about support. Broadcom, AMD, as well as NVIDIA supported. And OpenAI has been sort of beating the drums about it because they're very proud of the outcomes that they got with it. And so we'll talk about that when we cover sort of fault tolerance, fault recovery, some of those mechanisms as well. Um, let's talk about going beyond observability. When we run these workloads, aside from seeing how they failed and or how they may fail, um, failure happens, right? So then when failure happens, there's two things you can do. One is you can say, well, the failure happened, we're okay with it because we're able to tolerate it. Maybe not ideal, but we'll live through it. The other one is obviously at some point you want to say, yeah, it failed. Let's quickly recover it. Your mean time to recovery. And if I can get that very, very short, then my cost, my wasted money of those 700 plus billion dollars that I put in there, some of that comes back to me because I haven't wasted all that money. Um, how do you view the two concepts in terms of fault tolerance versus failure recovery? And how should a network designer, network engineer, or someone building AI clusters think about that? And I'll leave that open to Suresh or Balaji. What's your thoughts about that?
I just to start, let's just take what do you do in a network where you're told in advance that the links are going to fail with a reasonably high probability? Okay. Well, you have to do something that's robust to that. And you know that you can't build in extra redundancy in the sense of having a spare links. You can increase the, fabric bandwidth to 1.2 times the offered load, right? Rather than keep it exactly subscribed. But that's, a different kind of expense. But maybe that's a sort of, it'll pay itself off, okay? Because then you can simplify the algorithms. So I always think of extra capacity in the fabric as a sort of a spatial speed up. When you build a switch, you can, what engineers, we call them as overspeed. If the line rate of the switch is 10 gig, if the fabric is able to transfer at 12 gig, let's say that's 1.2x speed up, okay? And so on. So most switches out there that have been built, let's say certainly in the 10G, 25G Ethernet world,
Hmm.
always have overspeed in something like 2x, okay? And we always think of that as grease. We think of this as the thing that makes the thing smoothly run along and not get caught up in like bad traffic configurations and stuff. Okay.
Hmm.
And spatial speed up is definitely one thing that would I would have preferred to have seen something of that type. Okay. Because what that allows you to do is to speed up requires you to do less algorithmic heavy lifting, right? You just get extra. It is what we call engineering factor of safety. Civil engineers used to do this for bridge building and everything. You design the best thing, and then you say, okay, I think I'm going to build in a factor of safety of 2. This has been guidelines from forever. Okay, and that's one thing that you could go and do. The other way is, of course, to say what does that mean anyway, right? If a link goes down, I have to rearrange the existing traffic onto other links, and I have to do that quickly, so I don't incur a lot of drops. And then, well, I have loss-free fabric in the sense that outside of failed links, I don't have buffer overflows because I have priority flow control. But that's sort of thing that tends to bite you when you're trying to reroute, and you can't distinguish between congestion and a broken link, and therefore rerouting very easily. So then you say, okay, let me go ahead and spray, which is the approach that MRC has
Right.
taken. And I think by the way, it is a working solution is always a respectable and a good solution. It's not, you can always argue, what's the other way of doing it, but when it works, that's a good thing. Okay. So I think just to say the last thing on it is basically, if you look at what you're now saying is I'm going to get the network and the end system to do two things together. One is to load balance together, and the second is to manage congestion together. Okay. The network has to send some signals like, ECN marks at a minimum.
Yep.
And you can say many of these are standard, but now they're used in non-standard ways. Okay. It's not the typical because the same thing is used for load balancing as also for congestion control. Okay. And so then now you sort of run the risk of overfitting the fabric design to the workload, right? This happened like when we had fiber channel, it was an overfitted solution. That's why it's pretty much gone away. And Rocky V2 took over that entire thing, right? It was cheaper, less maintenance, less overhead. You don't have to have two separate networks, all that, right? And that's also why InfiniBand is going to yield to Ethernet ultimately, right? And so an overfitted solution is what I feel sometimes that we've arrived at. That's not a bad thing in the short term because other work needs to be done. We don't need the network to hold up the greater good of AI advancement, okay? But there's a certain chapter coming just down the line as far as I'm concerned, right?
I think I'd say so. There's two threads here, right? On the first thread of failure recovery at the component level, at the fabric level versus at the workload level. I think of sort of network failures. There's sort of withstanding links that are bad, withstanding failures that happen at the underlying fabric level. It's like basically dealing with turbulence. But workload failover is like dealing with impact, right? And so you've always needed to basically make sure that you could deal with transient or localized faults in a manner that doesn't propagate up. That's always a great thing to do. Whether that's memory with error correction, whether that's RAID subsystems where sort of parity allows you to not propagate a fault up into the file system, or whether that's in the ability for MRC to reroute around fail links and not let that propagate up to the application. It's great to have, and frankly, the first line of defense. And in this way, MRC has made great strides from where Rocky V2 has been, whether it's in congestion control, borrowing from some of the constructs of UET, or whether it's in the area of really fast fault isolation and rerouting. In addition to performance, I would argue that MRC has made the greatest strides in being able to deal with localized failures really well. What that doesn't still, and so I would argue these are complementary. What doesn't still allow you to do, for example, is if I have a complete failure, let's say a switch or what have you, or a GPU has failed or something more catastrophic has happened, the workload still needs to make sure that it can survive those kind of hard failures and continue in a manner where the application doesn't grind to a halt. I don't have to go back to a checkpoint if it's training. I don't have to recreate KV state if it's inference and lose latency for serving requests. And so there's a sort of they operate at two different layers, both complementary, I would argue, and both necessary. There's a different sort of an interesting question on sort of MRC, its state in the evolution of transport, if you will. That's slightly different from the whole question. And so I will say, at a time when you're making investments to the tune of 700 billion or a trillion, eking out every percentage point of efficiency is so valuable that in the short term, it's going to make things a lot better. What I worry about is the proliferation of complexity. So let me give you sort of what I mean. So front-end networks have been different. For training, MRC, I would argue, is a superior alternative to the Rocky V2 as it stands today on many, many dimensions. And yet, it does not support all of the RDMA operations. So if I'm starting to go towards mixture of expert models where I need atomics in my collectives, then MRC does not support atomics. MRC does not support read operations. It does not support send or receive. And so you're now starting to say I can use MRC for a certain class of applications. It's a large percentage of nickel operate training, but not everyone. So I now have to start thinking about it doesn't support inference read from KV cache. It doesn't support pre-fill to decode movement for inference. And so now I'm starting to say, do I create yet another, just even for GPU to GPU communication, two kinds of RDMA fabrics, one which MRC supports and one which MRC doesn't support. And then we have not yet dealt with the fact that storage itself is starting to move towards wanting to use more and more RDMA, especially for things like fast KV cache reads in inference or really fast training ingestion. And so one of the questions I have is in the long run, are we going to have to fragment the fabric so much that it's no longer a common substrate, but we are really making it fine-grained and suited to individual workflows and use cases? That feels wasteful in a larger sense, even though in the short term, I think that's the right way to extract so the maximum efficiency out of your big GPU investments that you're making. And so it's a philosophical question, right? Which is I've always thought that innovation in technology has happened in horizontal layers for a good reason. People can move fast when they don't have to have intricate tie-ins between in a vertically oriented stack. But that's what we're starting to evolve to is lots of little vertically fine-tuned stacks. Over time, I think software will probably win out over extremely tightly co-designed vertical stacks, if you will.
Yeah.
Yeah, actually, can I just say one other additional comment on
Yes,
what
go ahead.
Suresh just said? The way I'm thinking of this precise comment you made about training and the choice of um, uh, nickel operations that are supported and so on.
Hmm.
The way I think of it is like if you think of something like the fabric for training and MRC as a candidate solution, it's really the best way to think of it is like it's a big switch. There's just senders and receivers, and you can unfold the fat tree, and then you get this big switch, right?
Hmm.
And into this big switch, it's harder to add the storage traffic, or because now it's subject to the same rules, right, of scheduling, or to have inference and KV cache come in, Okay. And so you end up having to think of this entire thing as one big switch, and then there's auxiliary networks off on the side in which some of these nodes are actually participating, not to mention the entire front end. Okay.
Yep.
And
Yep.
so ultimately, my experience with some of these things is literally, if you look at the data center networking evolution from the early days of data center bridging, the standards discussion, it
Mhm.
was the case that people were thinking of there were literally two or three separate networks embedded in the different Ethernet priorities. Okay, they lived by their own rules, and the switches and the end systems respected those rules, right? And that's how we went at it. But over time, they converged. I mean, in
Yep.
fact, the first
Yep.
entities that stripped away such distinctions were the hyperscalers, right?
Mhm. Yep.
Notably Google, Amazon, all the, and then of course Azure still has storage in RDMA class, but because it just at scale, this becomes how many networks do you really want to build, right, and
Agreed.
maintain? And so,
Yep.
yeah,
Yeah,
I mean,
I
what
think
is,
there is
sorry,
overhead. No, I
so
was going
sorry,
to say
we could keep going on this topic, but
Oh
no, go
yeah,
ahead.
no, I think we can. I mean, look, I think it's important, which is that I mean, it is philosophical, but then there is a pragmatic reality to it, which is that if I have that much money in this way, and I find that in order to get the optimization I need out of that workload, which for me is critical because that's where my returns are on pre-training, getting the model out is important. Then I go down with the extreme co-design principle, which is what's dominating right now. And extreme co-design says, for my specific workload, which we'll talk about in the next theme, right? Which is for this workload, I know exactly what I'm doing. And in that case, I will optimize everything from the top to the bottom down to the network level for this specific workload because it's important to me. And I believe that the returns are worth the complexity for the time being, right? For the
no, but
time
Roy,
being.
just equally, let's
Yeah.
not forget that Anthropic and Gemini are not on MRC right now, right? There are two major
That's
models
that's
of
right.
equal
That's right.
strength. Okay,
That's right. That's right. That's
and
right.
I would even add Meta when it was doing its Llama,
That's
because they're
correct
pretty
with
big,
Llama. That's
right?
right.
And
That's right.
so, it's borne in mind. That's not the only way to slice this.
Yeah, I mean, there's many. I mean, look, yeah, I mean, look on the Gemini, on the TPU, the networking clustering, the topology, the way that's there are different ways of attacking the problem, and this is a very specific OpenAI, Broadcom, Ethernet, pre-training this particular model, right? This approach to it, and
Think what it really emphasizes is even in transport, you're now basically in a world that's highly heterogeneous. I don't mean just at the hardware switch provider level, but in terms of the underlying transport technologies that are riding on top of the same NICs and the same switches, there's now heterogeneity, right? So when you think about what does it take to manage workloads like training and inference, observability in the net fabric has to start from what is the workload impact. Can I break that down into where in the fabric do I have a problem that's being manifested as an impact on end user latency, end
Mhm.
user throughput? And that has to work across MRC, across UET eventually, across Rocky V2, across InfiniBand, adaptive routing, or non-adaptive, or DLP, right?
Yeah,
And
yeah,
so when you step back and think about observability in the fabric, every network monitoring solution has been native to a single vendor. There have been
Mhm.
very few that have cut across and provided a heterogeneous view on how do I quickly diagnose problems and make sure my application is resilient to challenges in the fabric. And so you're going to require the ability to have observer. Similarly, fault tolerance at the component level and transport technologies for recovering from links and grave failures will
Mhm.
embed themselves within the transport.
Yeah,
But the
yeah,
moment you have something that has a higher blast radius, that has to work in a heterogeneous context. We have to recover training and make sure it's non-disruptive, whether you're running on MRC or on Rocky V2 or
yeah.
InfiniBand
That has to
and
be able
so
to
on. So I
recover.
think it
Yeah.
emphasizes that the layer above the transport becomes even more important when you have such a flux in transport technologies to provide a common user experience. Maybe not for the foundation labs that will build bespoke solutions, but for everybody else in the world,
Yeah.
you're going to have to
Yeah.
build sort of heterogeneous software
Yeah.
solutions, is my view.
I mean, an enterprise that's not OpenAI, that has
Right.
still a significant workload. I mean, they don't have 100,000 GPUs. They have a couple of thousand GPUs. It's still
That's
a
right.
problem. Maybe they have 10,000 GPUs. It's still a
Exactly.
problem for them.
Exactly. And
And
that's
they
true
don't,
for
yeah.
neoclouds that are
Yeah.
serving some part of their infrastructure is geared to neoclouds. A
Yeah.
larger, increasing part of their infrastructure over time will be for inference, will be for people doing training, not at the foundation lab scale, but enterprises doing that as well. And so that's where I think we'll keep going.
Yeah, agreed. And some of these techniques are sort of agnostic, right? Having a multi-planar approach, for instance, right?
Right.
To have, that gives you the tolerance, regardless of what you're running over that, right?
Indeed.
That's an
Indeed.
architectural topology-based, approach to that.
Indeed.
I'd actually add the high radix idea is a good one
Yes,
because
high radix, exactly.
when you have a total, switch aggregate bandwidth, switching bandwidth, it's better to have many ports and
Yeah.
make the port speed smaller. That's a good idea.
Yeah, yeah.
Indeed.
So these are independent, and those are all good ideas of approaching it. I mean, some of the MRC stuff with congestion control, be the selective ACK, NAC versus go back N. I mean, those things
Those are
add some elements.
valuable.
These are all valuable, and I
Yeah.
think those definitely will bring it. And that's regardless of what you run on top and how you
Indeed.
approach it. I think that
Indeed.
is valuable. But I think where we're getting into is theme number three, which is that given where we are right now, given the importance of these workloads and the expense or the value that's created with these workloads, that understanding the workloads in addition to the context of workload awareness is really important, right? And the network needs to support that. I mean, in some ways, I think Suresh, you really brought up some of these. You brought up some of the talking points here for this topic, which is that whether you're pre-training, whether you're doing inferencing, the network is architected differently. We talked about the fact that maybe we have different networks for different workloads for the time being. I think that's one of the elements. I'm just going to pause here and be right back. Sorry. Um, Speaking of network, I need MRC for my WAN is what I do.
That's right.
Anyway, so I need multi-planar WAN.
Only
Um,
when you're talking, not when you're listening. No, I'm
When
sorry.
then, no, yeah, exactly.
Right, not read.
It's exactly it's a right problem. I have a right immediate problem on my video is what I have, right? And MRC can help with that, right? So anyway, speaking of that, um, but then if I'm a network operator, if I'm a neocloud, right, and my network needs to do a couple of things, right? Where does how do I build this workload awareness into my network design, right? How do I approach it, right? Because it, enterprises come to me. I'm a neocloud. I have 10,000 GPUs. I have 20,000 GPUs, right? How should I think about this problem? Because enterprise one day will come and say, I want to run a little small pre-training. I need 5,000. Tomorrow, hey, I want to run inferencing. And by the way, how do I optimize my KV cache, right? How do you advise your clients to think about it? I mean, given,
Yeah. Yeah.
you sort of have a fault tolerance observability solution, right? That actually is workload aware now, and increasingly workload aware, right?
Yeah. Indeed. Indeed. I mean, I'll just chime in and then jump in, Balaji. I'll start exactly where I made the last comment, which is philosophically, it bothers me that we are fragmenting what should be a common resource into so much application specificity. And generally speaking, when I look historically at technologies that have evolved in such a sort of tightly coupled way, they remain brittle, and over time they break down into more innovation that's sort of makes a common substrate appear. So that's the first caveat I'll offer. The idea I do think there has always been some amount of workload awareness that's been inevitable to some degree, right? And so, for example, the world has accepted that GPU to GPU communication needs to happen over a dedicated backend fabric for training and pre-training in particular. The world is, and sort of segregating storage and front-end traffic out of the backend GPU to GPU was an easier step that most people took for granted. That's becoming a little bit more complicated now with inference starting to call into question the need for GPU to GPU traffic, even in inference workloads. It's with pre-fill disaggregation separation, you're starting to have sort of backend communication for inference, where the need to offload KV and move KV, especially for interactive inference workloads, where KV state can be the difference between sort of latency budgets being met or not. That's starting to dictate that I need a slightly different optimization in my backend network where latency rules in the case of interactive inference. Batch inference is starting to say throughput is what I care about deeply. And so, and protecting the output and storage movement is what I care about more deeply in batch inference because it can be very large context and so on, right? And so what you're now starting to say is, how do I First question, do I fragment the fabric into dedicated answers for each of these workloads? And one argument for doing so would be that each one of these has such a high investment level for me at very large scale that I'm spending so much on GPUs, I don't want to skimp on my network. I'll create five different networks. But what you pay is in terms of operational complexity. And over time, I think if you hardwire your economics with this much fragmentation, then ROI on your AI investments is going to be really hard. So fundamentally, where I come out, and this is sort of a lot of investments. So Clockwork has made investments in observability across fabric types, fault tolerance to survive any kind of failures. The next horizon and something that we're doing is to say, how do you take a RDMA fabric and really deliver software-driven quality of service for these different workloads without relying on fragmenting the fabric, right? And so that's sort of where I believe ultimately where you want to go is to not cause more fragmentation than is necessary. Some will make sense, but not one that calls for six different fabrics for storage, for batch inference, for interactive inference, for pre-training, and for front end, right? And so that's sort of where I go, which is you do want workload awareness. It's a no-brainer to say tensor parallel
Mhm.
should sit inside a scale-up system. Pipeline parallel movement may be okay to go between nodes on a scale-out network. Checkpoint moves may be okay to go across buildings. I might have a different building where I'm housing my training data from, where I'm doing my training, etc. Some amount of that placement and topology optimization makes total sense. But when you start to really make big hardware decisions based on workloads, I'm not sure that's the prudent path to take.
Yeah, I think
Yeah,
that's fair.
I think the distinction really here is between the enterprise, everything Suresh is saying. Think of like these large city scale bakeries that are, you know, now everything can be optimized. You squeeze out the most efficiency from your croissant things and your, just sliced bread of the wheat and white and whatever. You can just source it. You can have assembly lines. It'll be perfect. You're optimizing for a different thing, including taste, by the way. I'm not saying taste is sacrificed. Okay. But then if you're a neighborhood sort of thing and you don't have all this, so you are going to be more, trying to get more efficiency out of the thing that you have, right? And so you have to sort of make things more fungible, more robust. And there's a bunch of teams inside large enterprise that are using a shared resource rather differently from, foundation model training type things or large scale inference serving for that matter. Here are teams that are internal to the company that are using this, right? And so this distinction is the key distinction for me. What the warehouse scale data center solutions post 2005, what we thought of data center bridging, how the Googles and the Amazons and the others evolved was distinctly different from how the enterprises evolved. Okay. And you can think of totally flat networking and stuff. And of course, the factory has become the standard way of thinking about it, but they're not exactly the same network. And I think such will be the case. People can't afford as many networks as there are workloads. That's just not sensible, right?
I think in a pragmatic way, I would argue if you think about the most painful places where the decisions are coming ahead of us, I think inference, as we all know, is growing extremely rapidly.
Hmm.
And I think inference is called an inference increasingly. There's a buy-in to the idea that I need to create a separate tier or a separate class of data for my KV cache. And
Yeah.
the question, and KV cache, in order to feed it to the GPUs, is best done over an RDMA network. And so the question that it's prompting is, does that RDMA network share the same RDMA network as my training, assuming that I'm sharing inference and training on the same cluster, which may be an option for really large foundation labs, but increasingly is too difficult. You want to share your GPUs for inference and for training if you're a sort of mid-sized enterprise or even a mid-sized training AI native company. And so if I do that, do I allow my KV cache traffic to share fabric bandwidth with Nickel? Do I allow pre-filled decode to happen on the same backend RDMA network? Or do I move KV cache and somehow accommodate RDMA and TCP on a front-end network? And so those are probably the most immediate questions. And I would argue that fragmenting that is not the right answer. There are technologies that allow you to do shared fabrics more economically and without compromising performance. And that's the direction that sort of it should be workload aware. Of course, it should be workload aware, but that does not translate into fragmented and segmented networks is sort of our biggest argument that I would make, or it becomes just harder and harder to justify ROI.
Yep. I think that's fair. I think that's one of the key things that the most of the webinar audience will not be in an open AI, will not be in an Anthropic, will not be, you know, training models or they will not of that scale anyway. And so I think the reality is that I may be doing fine tuning, I'll be doing inferencing a lot more as an enterprise for the most
Right.
part, and the neoclouds will be serving those customers, right? For primarily, well, assuming that haven't they don't have all their capacity bought up by the frontier labs who are going around and buying up
Indeed.
all the neoclouds
Indeed.
capacity because that's where NVIDIA landed the GPUs. If that's not the case, um, I think that that's perfectly reasonable that you will build a fabric. I think regardless, observability and workload aware observability is
Yes.
important.
Yes.
I think the from a lessons learned, at least my takeaway from today is lessons learned is observability is really important, regardless of what you're doing, regardless of which domain and what workload. Number one. Number two, observability with regard to workload awareness, because it is important, and having the context is important. Understanding what went wrong, how and where, and what the impact is. I think that's important. I think that's key. Along with that, given the complexity of these networks, some kind of pre-run diagnostics, pre-run health checks, I think as a best practices, some of the key things. And then on the network architecture side, it seems like there are some best practices regardless, right? I think as we said and Balaji pointed out, multi-planar networks, right? High radix approaches. Some of these things you should have anyway. You should apply anyway, right? I think that just makes sense, right? And I think those we'll see. And with regard to the sort of the high level transport level directions, congestion management, congestion control, different techniques, smarter techniques, selective ACK, negative ACK versus, go back. And some of these techniques will be built in, regardless of what you're doing. They add value anyway, right? So looking at ways of applying that prior to getting to UET, if MRC makes sense, apply MRC. But I think the longer term for a more unif- unified approach, right, for networking. I mean, UET, yes, there is a migration to Lib Fabric. Yes, there is cost involved in getting there, but in the long term, it seems like that is a better target collectively, a more universal approach to it that doesn't just
Indeed.
support the current workloads that we have. I think that seems like some of the key takeaways here. And that the reality will be that because of the cost of GPUs and XPUs, because of the importance of both training and inference and in the between the fine tuning and reinforcement learning workloads, that there will be technologies designed to provide you with fault tolerance and faster recovery that are workload specific. There's no way around that just because of the importance and criticality of these workloads. This is not a web query, right? This is not a simple search. This is not a, plot me path A to path B. It, these workloads are expensive. Checkpoint is expensive. Going back 30 minutes or an hour is super expensive multiplied across 100,000, even 10,000 GPUs is not cheap. And so that's, I think, the expectations that we'll see more solutions around that, not dissimilar from the ones that Clockwork has, for instance, right?
Indeed.
That,
Indeed.
yeah.
Indeed.
Yeah. So we have a couple of minutes. I don't know if the audience wants to ask questions. They're welcome to. Or I know that the Clockwork team, I mean, they've always been very patient when I ask stupid questions. And so you're welcome to send them your questions as well. I'm sure there's a way to reach Suresh and Balaji. But any sort of final thoughts or summary that you want to provide to the audience, Suresh and then
Yeah,
Balaji?
I think I'll let Balaji go, and I'll say a few things. I think for me, there are four things that I'd sort of say that are key. One, I think heterogeneity is a given, and transport heterogeneity is not something that I thought as much about beyond InfiniBand and Rocky 2 years ago, but that's adding to the already existing trend towards heterogeneity. That's the first thing I would say. And that's not just at accelerators now, it's fabrics and everywhere. Second, I think our thesis on observability is irrespective of what the underlying fabric looks like. Start by measuring what the impact is on the workload, which is at the edge, on the servers, what's running on the servers, and what is the workload impact. Work your way through to saying, is the first question, is the network or fabric causing workload perturbation? If it is, figure out how you go from the network is responsible to the specific fabric element, whether that's a link or a port or a switch. And so our observability is geared towards start at the edge and triangulate to the specific point in the fabric that you need to really go examine more deeply. And that I think will be even more necessary as transport proliferate. Third, I think that I would say expect better and better failure resilience at the component level, whether it's through fast recovery to link flaps and gray failures at the fabric level, or better recovery to memory errors on GPUs and so on. But given the bounds that we are pushing on computing, failures are a fact of life, especially with such large scale synchronous clusters. And so you have to invest in workload fault tolerance if you want to have a high ROI to the investments you're making. So that's the third comment I'd make is expect resilience at the component level, but build fault tolerance at the workload layer. And the last comment I would make is it's necessary to make the workload understand the fabric and the fabric understand the workload. We are in that environment where optimizing both together is necessary. But I think over time, software that allows for heterogeneous traffic types and heterogeneous workloads to ride a common fabric. That's where the industry has always gone, and we'll get back to that. But in the interim, workload optimized fabrics seem like a given for some time.
Yeah, I think that's very fair. I mean, co-design right now, extreme co-design, which is where we're in the era, it points to the importance of trying to monetize that GPU you just spend,
That's right.
millions and trillions of
That's
dollars on,
right.
I guess.
That's right. That's right.
But in the long term, we shouldn't be breaking abstraction and layering, right? I mean, it's not cost effective to break layering. It is a
Yeah.
fundamental CS concept, and we should build on layering and abstraction. But for the time being, we'll break it just to make money. But all right. So, anyway, Valachi.
Yeah, I think yeah, I completely agree with whatever you guys have both said. But I think the thing to say is when something needs to be solved with great urgency, you're allowed to break a few things.
Yes.
And it's okay because you're either doing that or you're holding things up. Okay,
Yeah.
so that's one. The second thing is in the longer term, for me, the takeaway is I worked on this what became the Cisco's Nexus 5000 switch, the switch and line card algorithms. From then on, I've had a sort of a love-hate relationship with switches and switch chips. I think they're great when you're working on them at the technical level, but the more you get them to do, the more the things you got them to do today, you will actually actively ask them not to do over time. I mean, this is sort of because the workload changes on you. The need for doing some things that you thought were good today go away. Okay. In fact, they get in the way. That's even worse. Okay. And so for me, there's enter an idea that let the switches be doing the simplest, repeatable, high capacity, high throughput work. Because at the end of the day, it's a switch, so it's better be just switching, right? And not get too fancy is a good idea. Okay. And in fact, let the transport happen from the edge and, use the smallest number of extra primitives you need. And anytime there's a good idea like ECN marking, just embrace it. Okay. But don't start overburdening it with like, well, I have 1 bit gives me some information. Why don't I get 2 bits on ECN? Why don't I get 3 bits? And now we're in sort of this ornateness. Okay. And so there's no need to get that far. Okay. The last thing to say is you notice that the buffers are going to get shorter and shorter and shorter.
Yeah.
Okay. And that's a resource that is going to just start biting. And Radix is not going to help us here. Okay. So just, I think there's a person who asked a question. And if so, we should leave some time for that.
Yeah, let's actually, yeah, we just had a question come in. So the question is, we spend a lot of time discussing the importance of AI infrastructure observability through the lens of networking and compute. As clusters scale, the physical layer is just as volatile. And the question here is, what should we be thinking about observability when it comes to, hardware, BOM, bill of materials variance, right? Mismatched components, firmware drift, environmental factors. I think and how do we correlate these physical facility level metrics with the traditional telemetry? That's a really good point. We know that many times we have the fact that the pluggables are not compatible with certain specific, switches or specific NICs, and we've all been there. And sometimes it's a gray failure, which is the worst case. So, and temperature, right? The environmentals are clearly important as well. So, any thoughts around that, Suresh or Balaji? Good question.
Well, I'll just say we actually, Balaji and I just met a company not more than a week ago, and actually just to name the company, it's Credo, and I was very impressed with the amount of telemetry that's coming out of the optical component layer that today has to be aggregated up through a switch, but we're only consuming a fraction of what telemetry is being exposed at that layer right now. If I step back and make this a slightly macro point, I continue to believe that you'll get a lot of sort of element level telemetry, right? Element level telemetry from switches, links, DOM metrics, and so on and so forth, right? And sort of so the question I think is how do I take this enormous amount of telemetry, and then how do I rapidly extract detections, and then following a detection, how do I get to root cause analysis, right? And so that remains, that's not an unusual problem. It's what we've done extremely well in the cloud. Companies like Datadog have aggregated signals from hundreds of sources in order to be able to allow someone else to correlate those. I think what is different here is that it's much more infrastructure centric. It's much more diverse, and really sort of knowing how to detect when something impacts a workload, and from there start to figure out exactly how to dive into the root causes. So I'm not sure. I don't think the technology approach is complex. The diversity of sources and the richness of telemetry is rapidly evolving. And so I do think we'll see a much, much, much richer set of signals that will be coordinated in centralized observability systems. That is certainly an aspiration that Clockwork is working towards.
Yeah.
Agreed. And the hyperscalers, a lot
I
of them are
think,
doing that, right?
yeah, I
Exactly.
think
Well, yeah.
my
Yeah.
thought on this is that, well, Roy, SDN and software-defined networking. The thought there was we will get switches to be programmable and do various things, special or different.
Yep.
I think the era of telemetry-defined networking is upon us, literally.
Mm, mm, mm.
The more informed you are about the network, the better you will be, whether there's traffic running or not, any connectivity and issues of that type, and traffic related things. Okay. How are some parts of the network doing? How are some components of the network doing? That really is going to be telemetry defined network. That age is upon us. It's pretty
Yep.
clear.
Yep.
And
I
in
think
fact,
that's
the
important. Yeah.
cluster mapper sort of thing component of MRC
Yes.
makes that totally
It
salient.
does. It does. And I mean, if you look at cluster mapper and some of the things that are done, it's fundamentally it goes back to software defined networking, right? And the telemetry that feeds the decision in terms of SDN, right? What goes into the control decision? It can
Yeah.
be anything. Well, not anything, but I mean, telemetry is one of that. Your
Yeah.
policy, your costs, right? And I mean, those are all components in that SDN. And fundamentally, you're absolutely right. I mean, if I had a completely configurable software network. I can segregate it, segment it, do whatever I want to it to optimize for the workload. And that was the intent, right?
But it's preceded by observations.
Yeah,
Policy is not independent of measurement, right?
that's right. That's right.
And sort of, yeah,
That's right.
that's really,
That's right. The closed loop measurement telemetry, that's always been part of SDN, right? The ability to take all that into account in terms of achieving whatever goal you want to achieve on the network. We're back to SDN again, just many, many years later. That's always there.
well, we're back to circuit switching. Let's start with that with
We're
MRC.
back to circuit actually, we're back to circuit switching. And in fact, the way you fix that is just put OCS, optical circuit switching,
Yes.
and we're all good, right? No, kidding. I'm kidding. So with that, I think we're at the top of the hour. Thank you, Suresh, and thank you, Balaji. This has been a very useful conversation. I think it's been I mean, I've learned a lot as usual in conversations with both of you, and I hope the audience has enjoyed it as well. But again, the audience, if you have questions, again, I'm sure you can ask a lot more intelligent questions than I can of the two gentlemen here and the Clockwork team. Been impressed with all my interactions with them, and hopefully you'll have a chance to speak with them as well on the topic of networking, observability, fault tolerance, and all things AI workloads, or not.
Thank you very much, all,
Thank
and
you,
thank
Roy.
you, Roy, for hosting this. This is
Yes.
very helpful.
Thanks, Suresh.
Thank
Thanks,
you.
Balaji. Thank
Bye.
you.